Hello everyone, welcome to this presentation. I am Kaustubh, and today we'll be talking about practical applications of machine learning. This session will be split into three parts. I will be conducting the first and last part, and Alex will walk us through data-centric machine learning applications and demonstrations around it. Now, before going into machine learning part of it, let's just recap on what we are dealing with in terms of data when it comes to infrastructure digital twin. We have data varying from GIS all the way to IoT data coming from asset performance and maintenance. You will have your 2D, 3D building information or design drawings. And you will also have the temporal aspect where a construction process or some other time-sensitive change is captured in your digital twin. Now, all of that data, needless to say, is compiled together and your digital twin is built. Now, the expectation with AI ML around digital twin is AI ML will help, machine learning will unlock the next level of reporting or next level of analytics where we will be able to find patterns and able to do some prescriptive things around design. And that's completely true. But the challenge, as you can see, with the various data sources coming together is of data alignment. Based on our experience of working with multiple users, may that be in the civil industry or oil and gas industry, data alignment and trustworthiness of the digital twin is the major concern. So before we jump into prescriptive AI, which can assist or optimize the design process itself, I think the bigger challenge in front of the industry is how we can use machine learning and artificial intelligence in solving our data alignment and the trustworthiness of the digital twin. Now let's look at data quality check workflow in the industry. As you can see, design changes will come in or some other data changes will come into a digital twin, and someone is tasked to review that information to ensure the information that's coming into the digital twin conforms the standards that has been specified by the owner operator or for some other government requirements or code specifications. Now, this entire workflow, when you have multiple data sources used in the project, your data formats coming across from various sources is different. This checking of data quality becomes a daunting task. And this is where I think machine learning can definitely help us to expedite the entire process, hence optimizing the design or just the digital twin creation part, and overall benefiting across the entire life cycle of that asset. So around this workflow, we have created a machine learning algorithm to detect misclassification in the 3D data, and Alex will be soon demonstrating that. Before I hand it over to Alex, I would like to emphasize the importance of taking staircase approach with AI and ML. The current challenge with the industry is around digital twin creation, the data alignment part, and the trustworthiness part. To make AI and ML implementation practical, I think it's important to focus on that foundational layer and build tools to assist engineers and information managers to efficiently create the digital twin, which is trustworthy throughout the life cycle of that asset. Once we cement that foundational layer, then the next challenge will be to look at cross-data silo reporting, where we are looking at project execution data as well as our design data and start thinking of insights and analytics around it. KPI forecasting detecting cost overruns or delays in the schedule. And a step after that will be the prescriptive design itself, or identifying a workflow or task automations. So with that being said, I would like to hand it over to Alex to show us some actual practical demonstration of data-centric machine learning applications. To you, Alex.
Thank you, Kaustubh. As you mentioned, machine learning brings a lot of promise to our industry. The potential impacts are hard to measure, but we foresee they'll be transformational. Value generated by these technologies mainly comes from information that's hidden in our data. It also comes from the expertise that allows identifying opportunities and building solutions that solve real challenges. Since data increases over time, value creation is compounded. And those that start soon might build an insurmountable competitive advantage. I'll give you the secret of companies that generate the most value from AI. It's quite simple, in theory at least. The leaders in AI make sure they have access to the data sources that contain information that will help them solve their biggest challenges. They're allergic to data silos. They're also willing to collaborate with strategic partners to generate data networks that will be hard to duplicate. Having access to the right data is not enough though. You also need to have data that's right. Kaustubh mentioned earlier the critical importance of data alignment and trustworthiness. I couldn't agree more with him. And finally, those that will have the courage of rethinking their work processes with the capabilities of ML in mind will benefit more than those that do not. I have good news for every one of you today. By using Bentley's digital twin technologies, you're ensuring that you'll be taking along for the AI ride. And your journey starts now. As you know, a digital twin of an asset is created by the aggregation of different data sources that make it possible to accurately and continuously represent the asset throughout its life cycle. Here, we show a subset of potential data sources on which we've been working to make the creation, maintenance, and exploitation of digital twins as easy as possible. I'll be presenting a few examples of projects that show how we do this. A digital twin gives you unfettered access to your most valuable data. Just by being able to visualize the state of your assets, you can start making better informed decisions. Machine learning can also help there. The technology can assist in many domain-specific applications by unlocking the 4 superpowers of advanced data analytics. Descriptive analytics to understand what's happening. Diagnostics to understand why something's happening. Predictive analytics, you guessed it, to predict what will happen. And prescriptive analytics to suggest optimized actions given a situation. The number of potential applications stemming from these capabilities is astounding. So far, we've identified more than 1,000 potential ML-based innovation roadmaps in different markets, and we're only scratching the surface. But as Kaustubh mentioned, to unlock all this potential value, we first need to concentrate on data integration, alignment, and quality. Let's take a closer look at 1D data. Dimensions are an example of 1D data. A lot of physical measurements, such as voltage, current, temperature, pressure, are also unidimensional in nature and are often recorded over time, thus creating a time series. The 1D data processing application I'll describe was presented by my colleague Andrew Smith in a Twin Talk last week. It consists in preparing and analyzing real measurements to predict the probability that a segment will degrade in a way that exceeds operational or safety thresholds. For those of you less familiar with the rail industry, it's important to understand that rail operation is highly regulated. Rails are regularly inspected with different instruments that are often mounted on special trains. In addition to protecting people, rail operators have incentives to maintain their network in good order, since the speed at which trains are allowed to travel on the rails is partly dictated by the state of the infrastructure. Increasing the average speed by 1 mile an hour on an extended network can have a positive impact of millions of dollars on the bottom line. Asset-wise linear analytics provides tools to analyze the rail measurements and to support decision-making for maintenance of rail networks. Here's how AI is helping with that task. Data collected during a survey gives spatial information about the track. A number of surveys are conducted at different moments. This gives us the basis to try to predict trends in track geometry over time. Before we apply predictive analytics, though, we need to correct for two errors that could affect the machine learning results. One is correction of position misalignments, and two is removal of outliers. Position misalignments are due to instrument errors. They can cause unacceptable spatial shifts and signal deformations. A technique that estimates residual misalignment and the uncertainty associated with that estimation can be applied to the signal. This allows us to fine-tune the signal realignment, which increases by 8% the number of points that can be used for analysis. Outliers can be caused by debris on the track or by instrument failures. They usually appear as high-frequency fluctuations in the signal. To be tagged as an outlier, the amplitude of the high-frequency signal does not need to be higher than that of normal measurements. We designed an adaptive filter that can locate outliers with an accuracy greater than 99%. Finally, we inject 18 track parameters in our proprietary ML model, and that model predicts sections of rail where the track geometry has a sufficiently high probability of exceeding the safety thresholds to justify preventive actions. And there you have it, an end-to-end predictive maintenance application using 1D data sources. Images and videos is the next category of data we're concentrating on. Some of the first applications using deep neural networks aimed at extracting information from images. Performances have since continued to improve. We are now at a point that we could argue that these applications have reached a maturity level that makes them well suited to enter the commercial world. At Bentley, we're putting deep neural networks to work on many image and video analysis applications. Context Capture Insights is a Bentley technology leveraging image recognitions through AI. Here, you can see a recent application where we are automatically extracting objects or regions from aerial images. This capability creates opportunities such as vegetation management, tracking solar panels deployment, and measuring ground coverage by detecting ground, parking lots, roads, buildings, etc. I think this one's a scoop. It's not been announced yet. Synchro Control, one of our flagship products for the construction industry, will soon be offering intelligent media indexing capabilities. ML models will analyze your construction photos to make them searchable by content, location, and time. You'll be able to visualize the results directly on the map of your construction site. This should help for issue resolution and progress monitoring. We're also building a suite of automated inspection solutions based on image and video analysis. For example, here, a machine learning model in Context Capture Insights detects cracks on a bridge and projects the results on a reality model of the asset. We're working on other types of detectors for inventory and inspection of assets. We should have interesting progress to report on that front at the next YII conference. This takes us to the final data categories. 3D models and reality meshes are definitively important components of a lot of asset digital twins. We're working on erasing the barrier that separates 3D models and reality meshes. Once this becomes a reality, We can take full advantage of the temporal evolution of models and meshes to work on applications around scheduling, progress monitoring, and quality management. I'll now present two exciting features that take advantage of 3D models and technical drawings to facilitate the creation of digital twins. The first tool is integrated in iTwin design validation. It automatically finds misclassifications of 3D model components imported into an iModel. In this example, the algorithm discovered components that are unclassified. The tool predicts that these components are probably pipes. A reviewer can select some or all of these components and attach an issue to them so that the designer can improve the model's data quality. But how does a functionality like this work? Before we can find misclassifications, we must be able to classify. Let's take a simple example. How would you go about classifying this object? You'd probably start by looking at it. What's its shape? What's its orientation? Here, you could hypothesize that this might be a wall. To make sure, you situate the part in its context. And you'd find that in this case, you are right, this is a wall. If you had access to the information, you could improve your decision by looking at other characteristics of the component, such as its dimension, its weight, its material. The more information you have access to, the more confident you'll be in the accuracy of your classification. With all that information, your job should be done, right? Well, there's still one more thing. You name the component a wall, but you need to make sure that this is how everyone names a wall within your organization. You must use a common schema for naming things in order to avoid ambiguities. Nomenclature can change from one domain of application to the next. Collaborators working on a project could even be using different names to identify the same thing. So, what would you do then? You probably consult past projects or ask a colleague to learn the standard naming schema used in your business. All of that just to classify one part correctly. Shows you how amazing the human brain is, right? We go through this effortlessly. However, it's inconceivable to ask that a person classify the thousands, if not hundreds of thousands of components that constitute a complex engineering model. It would just take too much time. Not to mention that you'd probably go crazy going through the process. That's where machine learning comes in. By providing to an ML algorithm many examples of models with pre-identified components and characteristics, it learns what makes a wall, what makes a pipe, and so on and so forth. It also adopts the right naming schema from the examples that are provided. At that point, the algorithm can start finding inconsistencies across the feature space of an object. For example, if most characteristics point to the classification of an object as a wall, but the material is something that's not usually associated with a wall, the algorithm can point that out. And it can do so at scale. Very complex models can be validated in a matter of seconds. The last solution I'll be presenting can be found in Plantside and AssetWise. The vast majority of revenue in the oil, gas, and process industries is earned from existing assets that have been in operation for more than 20 years. As such, technical drawings associated with these assets can often only be found in non-intelligent formats such as scans and PDFs. This makes it inconvenient for owner-operators to integrate these important sources of information in modern digital workflows. Bentley has developed solutions to help owners quickly build digital twins from the information they have today. For example, we can see here a new ML-powered feature that can extract meaning and understanding from process and instrumentation documents, or P&ID in short. These documents are the key to understand how the different components in a plant operate together. While many companies are currently spending days having humans painstakingly recreate each raw document in a design application, our approach completes this task in mere minutes. This technology makes the benefits of digital twins immediately accessible to existing plants and unlocks latent value for users. The migration process starts with non-intelligent technical drawings in raster files, such as PDF or image formats. An optical character recognition algorithm first extracts the text boxes of the drawing. Then, the drawing goes through a series of proprietary neural networks. The first one recognizes a variety of common symbols found on PNID documents, no matter what the symbol palette is being used. A second neural net then predicts different properties associated with the object. For example, for a valve, we predict its type, its openness, and its failure behavior. A third network associates the text boxes obtained from the OCR with the symbols to which they refer. And there you have it. The file can now be integrated in the digital twin technological stack, and you can start unlocking the previously inaccessible information hidden in it. And that's it for me, folks. Stay tuned in the coming months and years as our teams at Bentley continue developing new ML-based applications to build a smarter future. Back to you, Kaustubh.
Thanks, Alex. To conclude, I would like to again emphasize on the typical place of AI and ML in data lineage. As we talked about the challenges that we are facing in the industry with digital twin and some of the presentation that Alex gave, it is very evident and at the same time very practical to start introducing machine learning or AI tools in the early steps of this data lineage, starting from creation of the digital twin itself to validation and generating reports. We can use machine learning assisted workflows in all of these steps. With that being said, I would like to extend invitation to collaborate with us on this journey. We're looking for collaborators that are willing to explore possibilities of AI in the different stages of the asset lifecycle. So please reach out to us if you're interested. And as a parting thought, I would like to quote our founder and chief technology officer, Keith Bentley. Keith, in his latest interview in Iran Infrastructure, stated eloquently how machine learning will revolutionize the entire life cycle of an infrastructure asset. With such a strong commitment from our CTO, I'm confident we will keep on pushing the bar around AI and ML applications in the digital twin. I really hope what you have seen today excites and inspires you, and thank you for watching this presentation.